Okay, Kaustubh is a MS-17 student and he's majoring in biology. He's doing his MS thesis in ecology and he shares equal passion for ecology and astronomy. He always has up-to-date knowledge of rocket launches, satellites, etc. And he's a go-to person to talk about any recent updates in the space flights. His pictures of the night sky and eclipses have been featured on a number of places on internet. You can find his pictures on Astro Club's Instagram page as well. In fact, the photo that you saw on the poster of this talk is also clicked by Kaustubh. And with that, I think I'll hand over to Kaustubh. It's to you, Kaustubh.
Yeah, hi.
Yeah.
Thanks for the introduction.
Yeah.
So before that, I am on my mobile network. So if I get logged out, so you can.
Yeah.
Okay. I'll also be like turning off my video to like
Sure.
preserve the bandwidth.
Yeah.
Okay. Yeah, is my screen visible?
Yeah. Can you try to make it full screen?
Yeah.
Yeah, perfect.
Okay, is this pointer also visible?
Yeah, the pointer is visible.
Okay, so I'll begin now. So yeah, welcome everyone to this talk, Introduction to Astrophotography. I am Kaustubh Verma from MS-17 batch. And yeah, let's begin. So this talk is divided into two parts. In the first part, we'll see the basics of how photography works, telescopes and lenses and cameras. And in the second part, we'll see how to use these devices to take astrophotographs. So before that, why do we need to do astrophotography? No, I don't need to tell you this because like we are all interested in astronomy. So, but anyways, the first thing is that there are several objects which you can't see with naked eyes. For example, you must have seen pictures of galaxies and nebulas, which you can't see in the night sky. They can only be pictured through photography. Next is that if you want to see some changes in the position of some object, for example, a comet or an asteroid, you will need to take pictures of that object over successive days to see how is it moving. And the third point, which is like quite, how should I say, like nice is that the photons that have been traveling for millions of years from galaxies from far away, now you are capturing those photons, and isn't that a very nice thought? So these objects that you are seeing, they are what they were millions of years ago. So they say that telescopes are like time machines. So the first part, the basics of photography lenses and stuff. So for those of you who do photography, must know that there are three aspects to photography, which are called ISO, shutter speed, and aperture. These three combine to make what is called an exposure triangle. So this determines the amount of light that is hitting your sensor. Apart from these three, there's also an aspect called focal length, which changes the field of view of your image. So let's talk about ISO. So the ISO can range from anywhere around 50 to 100 to around more than 20,000 to 5600. In modern day smartphones, this can only vary up to a limited range of around 3,200 or 6,400. Now, a lower ISO means least sensitivity to light, but it will result in a better quality image, and it will have a least amount of noise in your image. Whereas higher ISOs will lead to a higher sensitivity to light in your image, but it will also lead to a lot of noise and the image will be of low quality. Modern day DSLRs can vary their ISOs from anywhere from 50 to around 2600 or even beyond. Now, shutter speed is the amount of time your sensor is open to the light, incoming light. This can vary from anywhere from around 1/8000 seconds to 30 seconds and beyond, which means that your shutter is open for 30 seconds, more than 30 seconds, or your shutter is open for only a fraction of a second. Now, a faster shutter speed will lead to less light hitting your sensor, but it will result in a sharper picture.
Excuse me.
Yeah.
I'm sorry to interrupt you, but could you please just explain what was that ISO? I missed that part. Just the explanation.
Okay. Okay. So ISO, like it's a measure of how much sensitivity, sorry, just a second. Sensitive your sensor is to your incoming light. So in older days, when you had reels and such, they used to come in different ISOs. So some reels used to be better equipped to handle more light, and some were specialized to uh, lower lights and higher lights. So when you change your ISO in your smartphone or in your DSLR, the sensor will change its working to like be more sensitive, sensitive to light or less sensitive to light. Is that
So is it it's related to the intensity of the incoming light?
it's more of a property of the sensor which changes, which allows it to become more sensitive.
Okay. Thank you so much, and thank you for repeating it for me.
Okay. So yeah, we are done with shutter speed. Now the aperture size. So the aperture size can vary from a larger aperture, which allows more light to pass through your aperture through your lens, and you can then vary the aperture size to allow less light in hitting a sensor. Now in astrophotography, we only use the highest aperture because we need more light to pass. We need more light. Now the focal length changes what is the field of view of your image. So if you you increase the focal length, it will produce a more magnified image, and it will give a lesser field of view. Smartphones have a very small focal lengths, whereas DSLRs have lenses which can vary their focal lengths. So in this example, you can see that on varying the focal length, on increasing the focal length, the field of view has decreased and it has got much magnified. Another example here is how the field of view changes with increasing the focal length from 14 millimeter to 70 millimeter. Now it is getting magnified, so the field of view has decreased, but we are getting magnified images. Now about telescopes and lenses. The resolution is a very important factor in image quality. The greater the resolution, the image quality will be better. The resolution depends upon the diameter of the lens or mirror we are using. It is inversely proportional. So the greater the aperture size of a telescope or a lens, the more it will be able to resolve. So here are the diagrams of the two type of telescopes that are present. One is refractive and other is Newtonian. Now, in astrophotography, there are two types of objects. The first one is the objects which are within our solar systems, which are the moon and the planets. And the other one are deep sky objects, or the objects that are present beyond our solar system. Now, you all must have seen the planets in the night sky. They are quite bright and are very obvious. But on the other hand, the deep sky objects, now these are very tricky and we can't see them with our naked eyes, just like that. Now the planets, they require a faster exposure time and a low ISO to capture. But the deep sky objects, they are very faint and they are impossible to see with the naked eye. Now, why is that the case? Why is that the case? Is because they are very far away, sometimes even millions of light years or thousands of light years away, and these are diffused objects, so the light is not very strong. So to properly capture these objects, we require high exposure times and a higher ISO. Now, one of the major misconceptions that people have is that they are not that they assume that the deep sky objects, they are not able to see them because they are very small. Now that is not the case. So here is the size comparison between Moon and Andromeda Galaxy. Now, if in the night sky, the Moon and Andromeda Galaxy were of the same brightness, then they would appear something like this. Now, as you can see, the Andromeda Galaxy is much bigger than Moon. But if you look at the night sky anytime, you don't see this picture. You don't see Andromeda Galaxy like this. Now, why? Because it is very faint and the light is not strong, whereas Moon is thousands of times more brighter than the galaxy. However, if you go to some rural place or away from the cities, you might just be able to make out the central bulge of the galaxy, which will appear as a fuzzy object. Now, to get a more sense of the relative sizes of these objects, here is the Andromeda Galaxy and the Moon from the previous example, and there are some other galaxies in here as well, the Whirlpool Galaxy, the Sombrero Galaxy, and here is the Ring Nebula. And finally, here is Jupiter. So you can appreciate how much small the planet Jupiter is with compared to the galaxies, the Andromeda, Sombrero, Whirlpool. So, and yet we can only see Jupiter in the night sky, and we can't see these galaxies, although they are much bigger than Jupiter. So about telescopes and such. Now, here is a very basic diagram of a astrophotography setup. To capture the light of the celestial objects, we need first a sensor, a lens or a telescope, and a mount and a tripod. So basically, the light that is coming from any object, it will be magnified by the telescope or the lens, and we will collect it on the sensor. The mount is used to uh, rotate our telescope to properly track the object in the night sky. We will discuss more about it later. Now, this is how an actual astrophotography setup looks like. Here is the telescope. Here is the camera sensor. Here is the mount. Here is the tripod and the counterweights. And here is a guide scope. You can have a host of other accessories installed on your astrophotography setup to increase your resolution, or maybe only get specific wavelengths by using a filter, etc. Now, first, I'll be talking about sensors. Now, a sensor is a very basic object which collects light and produces an image. Now, these sensors you will find in your smartphones, in your cameras, in your webcam, and some manufacturers also make special astronomy dedicated sensors. Now, these sensors are prone to get heated up when used over a long period of time. So that is a downside. We sometimes need to cool them to prevent this noise. Coming to mounts, there are three types of mounts. The first is the very basic alt-azimuth mount. Second is equatorial mount, and then is computerized mount. So the first one, the alt-azimuth mount, is a very basic type of tripod, which you also use in your cameras and the very basic cameras tripod that are available. It only goes from left to right and up and down. And you can't track objects, and hence you can't use it for long exposure astrophotography. Now, the equatorial mounts, they can track objects for a long time, and hence they are good for astrophotography. although they are heavy and need to be aligned every time we are having a session. The third type, the computerized mount, they are the easiest to operate yet very expensive. And with the push of some buttons, it will track the object for you and locate the objects. Now, type of telescopes or lenses, there are two types. The first one is a refractor, which is the very basic type of lens or telescope. Now, if you have a DSLR with a telescopic lens, then that is nothing else than a refractor telescope. These are cheap, but have a lower resolution, and hence they cannot be used for uh, heavy astrophotography. On the other hand, the Newtonian telescopes, they have higher resolution because they have a very big mirror inside them, which increases the resolution, the aperture, and they are good for astrophotography, but they can get heavier and a bit tricky to use. Other than these, the things I have mentioned, you can also use a binocular or a Dobsonian telescope for astrophotography. Binoculars are very versatile, cheap, and easy to use. You can also use them for terrestrial observation when you are not using them for astronomical observations. There are some binoculars which are dedicated for astronomical use. They have a higher aperture and they are heavier. You can use your smartphone with your binocular to take images of moon planets. There are specialized adapters that are available in the market. Other advantage of binoculars is they give a wider field of view. And coming to Dobsonian telescopes, these are popular type of telescopes that are used by people. They are relatively less expensive and offer a high resolution, although they can't be used for astrophotography because long exposure astrophotography because they don't have a tracking mount. Now, why do we need to track objects in the night sky? So it has to do with the rotation of the Earth. Now, you must have seen pictures like these, the star trails. They are produced by just keeping your camera at one point, focus at one point, and letting it run for several hours. So because of the rotation of the Earth, the stars, they appear to trail. But if we want to take picture of any specific object, this is very bad for us because it will trail and we can't get to focus. To counter this, we need an equatorial mount. Now, you may know that the rotation of the Earth is uh, on the right season axis. There are two axes, celestial axis, declination and RA. These are analogous to the longitude and latitudes on Earth. So the rotation of the Earth is on RA axis, and the stars, they appear to move on this axis. So an equatorial mount is designed to track the rotation of the stars on this axis. Once properly aligned, this type of mount can focus the star or any object for a very long time, allowing us to take higher exposure photographs. Next up, we'll be seeing how can we use these different equipments and telescopes to take astrophotographs. So first of all is the smartphone astrophotography, which is a very basic one. You can use your smartphone on a tripod to take pictures of star trails, or you can also use it to take pictures of Milky Way. On the other hand, if you have a telescope or a binocular, you can use an adapter to attach your smartphone to it and take pictures of moon and planets. You can get quite reasonably good pictures of moon with this setup. You can also see the moons of Jupiter with this setup. Now, coming to the DSLR astrophotography, this is also a very popular form of astrophotography. This doesn't require you to purchase any telescope. You can use your DSLR and your telephoto lens. So if you just have a basic tripod, you can use it to get star trails, Milky Way, and you can also use it to get some planets like Saturn and Jupiter, although with not much detail. On the other hand, if you can get somehow an equatorial mount, and then use your DSLR with that mount, it will open up a lot of possibilities. Like you can take pictures of some brighter nebulas like this Orion Nebula, which I took several years back, or pictures of comet and star clusters. You can do this without the need of any telescope, just by using the lens that is given with the DSLR. Now DSLRs in themselves are very good if you don't want to purchase any telescope, because they can be expensive, the telescopes. Now these are some of the images which I have taken over the years using only my DSLR and an equatorial mount. So a lot of deep sky objects in there as well: the Orion, the Andromeda Galaxy, Lagoon Nebula, Triangulum Galaxy, and a lot of star clusters. Now, but if you can get a telescope and get it to use with your DSLR, then nothing can be better than that. However, this setup costs some decent amount of money. You can get faint galaxies, globular clusters, nebulas, planets with much detail. You can even take pictures of the International Space Station with this, and much more. Like, there is nothing you can't take pictures of with this setup. Now we'll see that how are these pictures taken and what are the steps that are followed. First of all, we need to set up our instruments. We need to unpack them from the packaging, and we need to align them, focus them, and collimate them. Then we need to know where is the uh, object of our interest located. We can do this by using softwares like Stellarium, etc. And once we know the position of our object, we need to locate it and center it in our telescope. Then once we have the centered it in our camera, then we can take um, trial pictures of it, then see that what is the best setting for the exposure. We can change the ISOs and shutter speed to see what is the best setting. Then once we have finalized on our settings, we can take light frames and dark frames. Now, what are these frames? We will talk about it here. The light frames are just the pictures of our object of interest, the very basic pictures. We need to take a lot of light frames if you are taking pictures of deep sky objects like galaxies and nebulas, because they are fainter. Now, once we have taken pictures of the object, after that, we need to take dark frames. Now, these dark frames are taken with the lens cap on. These are just black images which have some information on them regarding the noise on the sensor. So as I told earlier, the sensor, it gets heated up. Now, if we take a completely black picture, the noise will still be there on the picture, but there will be nothing else. So after taking these light and dark frames, we'll use a special software where we'll put all these pictures together. And this software, what it will do for us is, it will stack these images. Now, what stacking does is that it increases the signal to noise ratio. Now, one individual image doesn't contain a lot of information, but if we use a lot of images, then the noise in each image will get reduced, and the signal or the photons that we are getting from maybe a galaxy or a nebula, it gets added up. So what the end result is we get a nice image of any object that we are observing. Then after this image has been stacked in the software, we'll use softwares like Lightroom or Photoshop to give finishing touches to our picture to make it more visually appealing. Now, stacking is a very important step in astrophotography. So if we are taking pictures of any object like planets, due to atmospheric turbulence and due to the small angular size of planets, the picture gets blurry. So we need to take a lot of images and stack them. As an example, here is a picture of an unstacked and a stacked moon. So in the right, on this left image, you can see that in an individual image contains a very blurry kind of moon, but when we have stacked them, the image becomes a lot sharper. Another example is here. The picture on the left is an individual frame of a Saturn, and after 1000 images that have been stacked, this looks much better and sharper. Now, stacking in the deep sky object images is a mandatory kind of. So I can give an example of an image which I took last year. So the first image is a single frame, a single raw image which I took of Andromeda galaxy. Now in this image, you can't really make out anything other than a fuzzy object in the center. Now, after stacking 75 light frames, you can see that some um, details have started to emerge. And after editing it in Lightroom, you can see that it is much better. Now, the comparison between one single raw image and the stacked image is, you can see right here, this image on the left. This has a lot of RGB noise and a very less amount of stars. This image on the right, it has a lot of stars and lesser amount of noise. Now here I have only used 75 light frames, but actually people use a lot of 200 or 300 or even more than that. And this image was taken in a light polluted area, so that's why it's not as good as the images which people take, and it is also a lot brighter. So when doing astrophotography, there are several things that we need to watch out for. The first is light pollution. Now, this does not have any impact on planetary imaging like Saturn and Jupiter and Venus. That doesn't affect it. But the light pollution is catastrophic for deep sky objects because it severely impacts the contrast on our images. Now, these DSOs are themselves very faint, and when light pollution comes, they are impossible to image. Now, second is moon. Now, when there is a full moon or a gibbous moon, that also causes a lot of light pollution. So the nights which have full moon are to be avoided, especially for deep sky objects. Third is cloud and fog. We can't do anything. The fourth is ground frost and dew. So on some nights when there is high humidity and you're taking images of with your camera, you'll see that your lens gets fogged up due to dew formation. Now this can be very irritating and time taking to wipe out the dew from your lens every now and then. To counteract this, there are some specialized accessories which will keep your lens heated up. Then haze and smog, which is also very bad for DSOs and planetary viewing. Now the haze and smog also acts kind of like clouds, but it is much worse because haze like decreases the contrast and like decreases the image quality. And the last thing is, which people don't realize until it's too late, are the mosquitoes, especially in summer. You have to have some mosquito repellent cream if you are going to sky watching session in summers. Now, what is the ideal time and location for sky watching? Now, time is especially spring season and autumn season are the best seasons for sky watching, and especially those nights which come after a rainy spell. So you'll see that after a rainy spell, the sky gets clear of all the pollution and smog. So that those nights are the best. Now, if you are doing some serious astrophotography, you have to go as far away from cities as you can, preferably some hill stations or some rural settings. You will see that most observatories are located on some desert-like environment or on some top of some hill, which is due to these factors. Now there are some threats to sky watching and astrophotography. The first of all is the light and air pollution, which I have mentioned. The second one is satellites. Now the number of satellites has been increasing every year, and this causes a serious ill effect on our on Earth-based astroimaging. Now, looking at the light pollution scale, there is a scale called a bottle scale, which kind of tells us how much of light pollution is there in our city skies. So the bottle one scale represents a very clear sky, which you can find in a very uh, rural setting or on some desert maybe. And towards the end of this scale are the city skies, which you will find in at the center of cities like Delhi or London, etc. So if you are talking about Mohali, Aisamoli, the sky lies somewhere around number 6. So this is the map which tells you how much light pollution is there at a particular location. This is helpful in knowing which places to avoid and where to go for sky viewing. You can see that the center of the Chandigarh has a lot of light pollution, and we are located on the suburbs of. So we have the northern sky we have is severely light polluted, whereas the southern sky is less so. So this is a picture showing the effects of satellites on uh, astrophotographs. So this is a wide-angle photograph of sky, and you can see that it has been ruined by a lot of satellites passing through. So we'll need, when you are taking astrophotographs, you'll see that a lot of images have these kind of trails. So you need to actively remove them, these type of images that are ruined by satellites. So if you have to take pictures from the city and you have no other options, then you will have to, you can use filters. Now these filters can block out all other wavelengths other than the wavelength in which we are interested. So this can severely improve our images. However, these filters are very expensive. One way of tackling this is we can take shorter exposure pictures with increased ISOs and then stack it. So instead of taking a 30-second exposure images, we'll take 10-second images, but we'll increase the amount of images we are taking by 3-folds. Now what it will do for us is that if you are taking a 30-second exposure in cities, then our image will be completely ruined because of light pollution. It will be completely white. However, a 10-second exposure won't be that much ruined. And another tip is that you should always wait for the object to reach the highest point. Now, the light pollution is always the least at the zenith. And so if you are taking the image at the zenith, then the image will be better. Also, as previously mentioned in this Chandigarh example, if you are taking any images, you should try to take when the object is towards the southern sky, because the light pollution is less in that area. So some general tips for astrophotography is that you should try out different settings, and you should experiment with whatever equipment you have and experiment and try out, don't hold back. So first of all, when you are trying, you will not know that which object is where. So it is crucial to use softwares like Stellarium to get an idea of where each object is located. And you should avoid overexposing your image. So one mistake which people make is that when photographing the moon, people take pictures of full moon, but that is to be avoided because the crescent phase is when the craters are best visible. So you should always look out for crescent stage of the moon for the best images. Now, some softwares which are commonly used for astrophotography are For star trails, you can use Photoshop GIMP, or there is another software called Star Stacks, which will take all your images and it will create a star trail image for you. For stacking planetary images, there is a software called Registacks. For deep sky object stacking, you can use Deep Sky Stacker. Now, these are free softwares, Registacks and Deep Sky Stacker. Also, StarStacks, these are free. And for editing, you can use Lightroom, Photoshop, GIMP, or any software. And as a planetarium, you can use Stellarium. Okay, that's it.
Yeah, thank you so much, Kaustubh. I mean, that was a wonderful talk. I think you explained everything that you have learned throughout your experiences in astrophotography in so many years. And it was a wonderful talk in general. So we can take questions probably now. So if anyone from the audience has any question, they can unmute and ask.
Excuse me, sir. When you shows the picture of map of Chandigarh, can you go to that?
Yeah.
Is the green place is better to for astrophotography?
So in this scale, you can see the radiance of the sky, which is the how much bright the sky is. Now, the more the light pollution, the brighter will be the sky. So the yellow and the reddish images are greater in this image, and in this image of Chandigarh, the red, purple, and white places are the most affected, and the green and the yellow images are less affected by light pollution.
Thank you, sir.
Where do you get these images from?
This is from some website called Light Pollution Map, I think. You can search map of light, like light pollution map, and it will show you some maps.
Okay.
So you mentioned about the trails that the satellites leave on your pictures. So suppose suppose we are taking multiple pictures and one of those pictures captured such trail. So what would happen if you don't remove that picture? I mean, would it prominently ruin the whole picture?
Yeah, it will, because you are stacking the images, and what the software does, it takes the brightest point. I don't know how the software works, but if you are stacking it the conventional way using GIMP, then it will ruin your picture. But if you are averaging out each frame, then the trail on one frame can get averaged out, maybe.
Okay.
Yeah, but it is best to remove the
Yeah.
images which have trail before you are stacking.
Makes sense. Does anyone else
Hello.
have any questions?
Yeah.
Hello.
Yes, yes.
So for the light pollution one, if we go to a nearby village like like the near one, and we find a place which is completely dark. So would you say there is light pollution? Because according to the map, we still say there is light pollution.
Yeah, rural areas also have a light pollution, but it will be much less than cities. So if you want to like totally avoid the light pollution, then you'll have to go somewhere where there is no one, like some uninhabited area.
Okay.
So maybe some mountains or some retreat or some trekking.
Okay. Got it.
If no one, I mean,
Yeah,
yeah,
hello.
yes.
So first of all, thank you for the wonderful talk, Kaustubh. Okay, so now to the questions I had. I had a few questions. So for first one is about the satellite thing that you told. So I wanted to ask, for example, if you're taking a very long exposure, because I've heard that people take exposures that amount to like 1 hour and in hours basically, single exposures that are for that much time, right?
Single exposure for that long, I haven't heard of it. Maybe more at max it can get for 2 or 3 minutes, but not for hours.
Oh, okay. So the maximum you take for is for 2 or 3 hours. Oh, sorry, 2 or 3 minutes.
2 or 3 minutes, yeah.
Okay, so is there a particular reason for that, like for not taking longer exposures?
So one is that if anything happens when you're taking the image, for example, if someone shakes your camera, and if someone any source of light, like some satellite
Okay,
or some
okay,
comes, so it will ruin your image. So
yeah,
to avoid that, will take a lot of, and also in light polluted areas, you have no choice. If you go beyond 20 or 30 seconds, then the image will be completely white.
okay,
So
okay, that's another reason. So I just wanted to ask, even if it's 2 or 3 minutes, say for example, you have a very short field, small field of view, right? And some satellite passes by and very quickly because it's a short field of view, small field of view. So say it takes 2 seconds for the satellite to cross your field of view, and your exposure is for 2 minutes, for example. So that's 120 seconds. So will how does it work? Will you still see a very prominent streak through your image, or will it get averaged out?
uh, there are some satellites which are bright and some which are not. So if the satellite happens to be a bright one, then it will leave a prominent trail. And in some cases, if it is a less bright one, it can leave a very faint trail which you can ignore maybe.
Okay, but is there an averaging out effect? Like, for example, will it be more prominent if it was, like, for example, a 30-second exposure rather than a 2-minute exposure?
No. So in the background, you have a dark. If you are taking it from a rural setting, you have the background as a dark sky. So
Yeah.
any point of light which comes in your image while you're taking the picture, it will appear in your final image. So
Okay. Okay.
it won't get averaged out.
Okay. 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 I got it. Because since this background is dark, it will get added onto it. But
Yeah.
say for example, in a more little light polluted skies, the background will have like a certain brightness, right?
Yeah.
And then it might get averaged out, right?
Yeah. Then it might.
Okay. Okay. Another question I had was, you said you capture objects when they're at their highest, so basically when they're crossing the meridian, right?
Yeah.
So you said that that's because you have the least amount of light pollution at the zenith, or basically at the meridian, sort of.
Yeah.
So is it the light pollution? Because as my understanding was for now was that you have the least amount of atmospheric disturbance that the light of the object has to pass through, or is the reason light pollution?
Yeah. Because more the light has to travel through the atmosphere, the more it will get disturbed because of the light pollution. So when the object is at the highest, it has
Yeah.
to travel the least amount of distance through the atmosphere.
Yeah.
So
So I mean, you'd still even if, like, for example, you go to a very remote place, you will still prefer the object at being at its highest point, right? I mean,
uh,
even
no
without
when
light pollution.
no when we are at a rural settings, then we will prefer any altitude, not necessarily zenith.
Okay, so matlab, the main factor is light pollution and not the atmospheric length it has to travel.
Yeah, it is due to the atmosphere.
Okay.
Because right now, if you look at the horizon, if you go out and look at the horizon, it will be very bright. And if you
Yeah.
look at the zenith, it will be darker. So it is because
Yeah.
the atmosphere is much thicker at that
Yeah.
angle.
I mean, you can like observe it with your eyes also. Like if you look straight up, you see a lot more stars, like a lot more fainter stars. Like if you look straight up for a couple
Exactly.
of minutes. Okay, so another question was, so I have a Dobsonian telescope that I use mostly for, I mean, for observational purposes. I can't really capture DSOs with it. So there's this one question have had in my mind for a long time. So can you use a Dobsonian telescope to take pictures of the deep sky objects? And like I have a method that I want to describe to you, but I'm not sure if it will work or not, or how to make it work or whatever. So what if you take very small exposures, like for example, 2 seconds maybe of a deep sky object, but you take a lot of them. So for example, if you were you showed the image you captured of Andromeda galaxy, right? You had 75 frames.
Yeah.
So what if I make it, for example, say 700 frames I capture over multiple nights, but each of them is like, for example, 1.5 seconds or 2 seconds, just enough to barely avoid the trailing. So will that work? Will I still get an image that looks as good as yours?
Yeah, that's what people do without when they don't have this tracking equipment. So
Okay,
I
so
have
it should
seen,
work.
I have seen a lot of people on Reddit post images of deep sky objects without equatorial mount. So they take 1 or 2 second exposure pictures and a lot of them and then stack them.
Okay, so I mean, then like do tracking, like having a tracking mount, like how does it help? I mean, if I can still do it with the DOB, like
So even if you are taking a 1 or 2 second exposure, some trail will still be there, but it won't be perfect, but it will be good. But if you
okay,
are using an equatorial mount, then it will be near perfect. And also
okay,
you are using, also instead of taking so many images, you can take less
yeah. So
image.
the workload is reduced. You mean?
Uh,
Yeah. Okay. So thank you. And that's all I had.
you should experiment with your
Yes,
Dobsonian.
definitely will. Thank you.
Hello.
Yeah.
Yes, you're
Yeah.
audible.
So one thing I wanted to like add to Sanatan's first question, like he asked about like longer exposure times, right? So I just wanted to tell in my experience, I had taken a few photos with like around 15 to 20 minutes sky exposure time with a DSLR. And I will tell you, never try that. It heats up the camera. That is one thing. And I was in a pretty dark place, so the photo turned out like okay-ish, and I got good star trails. But there's still a lot of noise from the background. Even like the faintest of the lights have, made the background sky full white. So like that's one thing. But the scariest part is the camera can get damaged.
Yeah.
Okay, thank you, Shantanu. I forgot about the camera heating part there. Yes.
Yeah. So 3 or 4 hours of taking continuous pictures can severely hit your camera. So some people have a cooling equipment which
Yeah.
they install in this setup.
The cooling equipment is mostly a fan, right?
Yeah, I
Is there
think.
more to it? Okay. So another question, I know now that Shantanu talked about noise. So uh, you said ki you can reduce noise by stacking. Did you say that, or like I'm confused here?
Yeah.
So how does that work? Like that's like you average out the values, is it?
Yeah, so let's say that in one image there is some bad pixel or some noise, some RGB noise, and one pixel is red, and or maybe any value which is like very obvious, obviously like ruining this picture. One any pixel here. So if you are taking 10 pictures and only one has a noise at a particular spot, so it will get averaged out.
Okay. Okay,
So
so how do then, like, I understand like how you can average out the noise by stacking, but then you said ki dark frames are also meant to, like, you basically subtract the dark frames from the light frames, right?
yeah.
So how will, because the noise will be random as I understand it.
Mhm.
So either you need like a lot of dark frames and then take the average dark frame and then subtract it from light frames. Is that what you do?
Yeah, so we take around 10-15 dark frames. So I exactly don't know how it works. I've only like seen it people do, so I also do it. So the sensors can produce some kind of patterns of noises which can be reduced by the stacking.
Oh, oh, so
Yeah.
the dark frame thing is meant for like systematic biases that your camera sensor might have towards noise. Ki like this region of your sensor is like generates a lot more noise. So you have patterns, so you reduce those patterns.
Yeah,
Is that
probably.
mean? Yeah.
And
Okay.
apart from dark frames, there are also like bias frames and flat frames for
Yeah.
more advanced form of removing the noise.
Acha. Can you explain those also, like if you?
Like I don't understand them fully, but the flat frames, they you take them by covering your camera lens with a white cloth and pointing it to some source of light, and then you take
Okay.
10-15 images. So what
Okay.
it will do is that whatever like dust you have on your sensor, that will get
Yeah.
reduced. So the images will produce an image which will
Oh.
tell the software where is the
Okay.
dust present in your sensor. It will then
Ah.
subtract it.
Yeah. Okay.
So if we don't have any more questions, then we can probably end this session. Also, before since people are leaving, we can keep discussing. But since some people are leaving, I'll just give a quick reminder for those who are on campus that if today's sky conditions are good enough, then those who are interested in learning all these things over the camera, and also maybe we can do a sky watching session. So you people can gather at the new basketball court in the sports complex at around 3 a.m., 4 a.m., whenever you wake up, probably. And we'll have a sort of hands-on session. And if the sky is not clear enough, then we'll inform you on the group at night. So are there any more questions?
Okay. So it's not a question again, but like a random comment. So the Kaustubh mentioned about mosquitoes, right? In some slide. So
Yeah, yeah.
to all the people who plan to go out and click pictures with their binoculars or telescopes, or even if they're with their camera, please do keep that in mind. We all learn that from experience, but good that Kaustubh here mentioned that part about mosquitoes. Do keep a mosquito repellent with you. It's very, very important.
Yeah.
Yeah, exactly.
Thank you so much, Kaustubh. Yeah, the talk was great.
Yeah, welcome.
Okay, so probably we can end the meeting now. And those who are on campus, we will see you at night. Okay, I'll end the meeting.